In this video, we discuss triple integrals and spherical coordinates. Now, we've discussed triple integrals in rectangular coordinates already and in cylindrical coordinates. Rectangular coordinates are sort of our default. We tend to describe everything in terms of x, y, and z. Those are directed distances from the xy plane, the yz plane, and the xz plane. But we said if we're dealing with a solid, if we're integrating over a solid region Q, and that solid region Q is easier to describe in cylindrical coordinates, because maybe the solid region Q exhibits symmetry about a line. So we see symmetry around something like this, kind of like you would with a cylinder. Should be a straight line, a vertical line, sorry. Then we might go to cylindrical coordinates, or if we look at the projection of Q onto the xy plane, if that projection happens to be a circular sector, we say, okay, maybe we should go to cylindrical coordinates, because cylindrical coordinates are really just polar coordinates plus z. We've got polar coordinates in the xy plane, and then we've got this z dimension that's giving us that symmetry about a line. So if we have a solid region that exhibits that symmetry, or the projection onto the xy plane is a circular sector, or if the integrand is more easily described in cylindrical coordinates. So that means the integrand itself has some symmetry about a line. So maybe the integrand involves x squared plus y squared, which means that the integrand is a function of r squared. That's the function of the distance from the z-axis. Then our integral might be better described in cylindrical coordinates. Spherical coordinates are similar, but instead of having symmetry about a line, I mean, it's just like you would imagine with a sphere. You've got symmetry about a point. So we will want to use these when the solid region Q exhibits symmetry about a point, or in other words, Q is part of a sphere. We also tend to use this when the integrand exhibits symmetry about a point, and usually that point is the origin in three-dimensional space. So maybe the integrand involves x squared plus y squared plus z squared, because if x squared plus y squared plus z squared is a constant, then we're saying the farther we get from the origin, well then the integrand is changing based on how far we are away from the origin. So if any of these things happen, we might want to use spherical coordinates. But again, the big picture with both of these coordinate systems is that if this integral is difficult to evaluate in rectangular coordinates, but I've got some symmetry about a line, so everything would be easier to describe in cylindrical coordinates, or I've got some symmetry about a point, so everything would be easier to describe in spherical coordinates, we just go to the alternate coordinate system. And these are just different ways of describing the same points. And in these new coordinate systems, the calculations can be a little bit easier. They're generally easier once we switch our coordinate systems. So So let's talk about the spherical coordinates conversion formulas, and then we'll talk about writing a triple integral in spherical coordinates. So instead of having a point x, y, z, we want to represent it differently. So let's say we're at location x, y, and I'm just drawing my little rectangular box to help me locate this point, x, y, z, and I'm going to draw it in the first octant. This distance from here to here is y, this distance from here to here is z, and the distance from there to there is x. Instead of writing this as an ordered triple x, y, z, I can write it as an ordered triple rho, theta, and phi. Now rho is the directed distance from the origin, or excuse me, not the directed distance, it's the strict distance from the origin. So that's my rho. Now theta is exactly the same theta from before, from polar coordinates. So if I make a line segment here in the xy plane to this point over here, like that distance we typically called r. That was r in polar coordinates. Theta was the angle that line segment made with the positive x-axis. So theta is an angle, it sort of sweeps around the xy plane. Now phi is a little different. And I actually looked this up before I made this video. There is not really much of a consensus anywhere. Is it phi or is it phi? Who knows? I read several articles and all of them were just going back and forth. Some of them were telling me the correct pronunciation was phi, and some of them were saying the correct pronunciation was phi. If I can't speak English, I'm gonna have trouble speaking Greek. But I think I'm just gonna call this, actually I might use them interchangeably. Sometimes I'll call it phi and sometimes I'll call it phi. Sorry about that. But both of them are pretty standard, and I guess it just depends on who you talk to. Dr. Constanda at TU knows the correct pronunciation of this. So if you want to know the truth, I mean, he's got other things to do, but I guess you could send him an email and ask him which of those is the correct pronunciation. I'm going to call it, I think I'm going to call it phi for right now. Phi is the angle that this line segment makes with the z-axis. I know, it's weird. You've got two different angles here. You've got an angle, which is just the same angle from polar coordinates. And then we've got this directed distance, or this distance, it's not directed distance, it's just the distance from the origin. So let's think about what each of these guys represents. I think it's helpful if we draw these points, if we label theta, phi, and rho on the outside of a sphere. So let's say we're here, we're on a sphere, and it's centered at the origin, and maybe that sphere has a radius of 3, just for example. Well, if we're at some point on the sphere, the distance from the origin out to here, that's rho. Rho is going to be 3. Now the angle phi is represented by this angle from here to here. Now there are a lot of different points that are making that exact same angle with the positive z-axis. There are actually infinitely many points. I'm going to try to draw a circle. So where phi is equal to a constant, what we'll have on our sphere is a line that looks like that. So all of the points that are making that angle with the z-axis are going to lie along that circle. And actually, it doesn't look quite right. Maybe it should be more like that. But where phi is equal to a constant, we're going to have lines like that. So if phi is a constant, we're going to have this. Oh, this is so ugly. I'm so sorry. But it's like these constants for phi and these constants for theta are like latitude and longitude. This is why I wish I had my sister's art skills right now. Okay. Yeah, it's bad. So phi is equal to a constant, we're going to be on one of these lines. Now, if theta is equal to a constant, well, that theta is going to intersect our sphere on a circle like this. So if theta is equal to a constant, these are really bad. You know what? I'm going to stop trying to draw these pictures. So theta and phi correspond to like latitude and longitude, basically. Because I can't do that all together on a sphere, obviously, I'm going to draw this a little bit differently. Let's say it this way. If rho is equal to a constant, we've got a sphere centered at the origin. So if rho equals 3, that's a sphere of radius 3. If rho equals 0, that's a sphere of radius 0, so it's just the origin. Rho equals 1, that's a sphere of radius 1. So rho equals a constant. That's a sphere centered at the origin with the radius equal to that constant, with radius rho. Now, if phi is equal to a constant, I know it might seem unusual, but what we actually get is a cone. Because phi is an angle that we make with the positive z-axis, an angle that that line segment makes with the positive z-axis. And if rho and theta are free to be anything, if that angle with the positive z-axis is constant, let's say we're going like 30 degrees this way, all the way around the z-axis, well, I'm also going 30 degrees that way and 30 degrees in the direction in front of us, like from here to there, and then 30 degrees behind us from there to there. It's the same 30 degrees all the way around. So this phi equals a constant is a cone. When theta is between 0 and pi over 2, that's what we get. I said theta. When phi is between 0 and pi over 2. If phi equals pi over 2, that means we're going to the xy plane. That's the entire xy plane. So that's the same as z equals 0. Now, if phi is between pi over 2 and pi, we get something like this. We get a cone facing down. The lower nap of that cone. Normally we have a double napped cone. This is just the bottom half. Now, if phi equals 0, that means the angle that we're making with the positive z-axis is 0. So it's just the positive z-axis, which is kind of odd, because what we're saying is x and y are both 0, and z is ranging from 0 to infinity. If phi equals pi, well, we're on the negative z-axis in that case. But generally, phi equals constant is going to give you a cone. So if the angle is between 0 and pi over 2, we get a cone up here. If phi is equal to pi over 2, that's just the xy plane. If phi is greater than pi over 2, but between 0 and pi, we get a cone down here. And if phi equals pi, we're over here. Now, some people say to me, well, what happens if phi is greater than pi? Well, if phi is greater than pi, let's say it was pi plus pi over 6, pi plus pi over 6, well, then it would be the same as going from here all the way to over here. So we generally don't do that. We always let phi be an angle between 0 and pi. So the possible range of phi values, these are angles made with the positive z-axis, are 0 to pi. So this is phi equals 0 up here, and here's phi equals pi down here. Okay. Now let's look at, we did constant values for rho that gave us spheres centered at the origin. Constant values for phi, that gave us these cones, or these blue lines that I was trying to draw on the surface of my sphere. Let's think about what would happen if we have constant values for theta. I think we all know what will happen. In the xy plane, if theta is equal to a constant, it looks like this. And that's that constant value for theta. If we've got this value for theta and r is positive, we go this way. If we have this value for theta and r is negative, we go that way. But what does that look like in three-dimensional space? Well, that looks like a plane. It's a plane that goes through the z-axis every time, because the z-axis is pointing straight up from this. Here's the x-axis, the y-axis, and the z is going straight up by the right-hand rule. So I'm going to try to draw a plane that passes through the z-axis as best I can. And that's theta. And that's theta equals a constant. So when theta is equal to a constant and that intersects a sphere, we get all of these lines. I was trying very hard to draw those lines, but unsuccessfully. Yeah, see, again, not very successfully. So it's like latitude and longitude, and rho is giving us the radius of that sphere. Okay, so how do these translate into formulas? Well, let's think about it. Let's go back to that picture that we were looking at earlier. If I'm at a location, XY0, and then we go up z units, so we're at XYZ. this would have been r. But now if I switch to spherical coordinates, that distance from the origin is rho. Just using my distance formula, I can see that the distance from the origin is rho, so that's the square root of x squared plus y squared plus z squared. And if I square both sides, I get x squared plus y squared plus z squared equals rho squared, which is exactly what we would expect. That's the equation of a sphere of radius rho centered at the origin. Okay, what else? Well, theta is still the same theta from before. So tangent of theta is still equal to y over x. And x can still be described by r cosine of theta, and y can still be described by r sine of theta. But r is not a part of our coordinate system anymore, so we need to get rid of r and get from r to phi. So you have to ask yourself, well, how is r related to, or excuse me, I said phi, but I want to say, how is r related to phi, and how is r related to rho over here? Well, it's hard to tell, but there's actually a right triangle right there. And the hypotenuse of that right triangle is rho. And if this angle, let me extend this a little bit. If this angle is phi, then that means this angle is phi. Just knowing what we know about angles from high school geometry. Also, you could do, this is phi, and that's 90 minus phi, and that's got to be this 90 minus phi plus that angle must be 90, so that must be phi as well. Okay, so what does that do for us? Well, r is opposite phi, or excuse me, yeah, opposite phi in this triangle, and the hypotenuse is rho. So using this triangle, I've got sine of phi is opposite, so r over rho. So I can solve that for r. R is rho sine of phi. So now I can use that to come up with my formulas for x and y. So x is rho sine of phi cosine of theta, and y is rho sine of phi sine of theta. Okay, and now we need to involve z in this somehow. How is z related to rho and phi? Well, z is this other side of the triangle. That's z. So z is adjacent to phi. So sine or cosine of phi is adjacent over hypotenuse. So z must be rho cosine of phi. Okay, so that's another formula. I know this is kind of messy, so I'm going to put this on another page. Let's flip it. Here are our formulas. So we've got x squared plus y squared plus z squared equals rho squared. We know that tangent of theta is y over x. And we just derived that x equals rho sine of phi times cosine of theta, because rho sine of phi turns out to be equal to r, that r that we used in polar coordinates and cylindrical coordinates. And y is r sine of theta, and r is still rho sine of phi, so we get rho sine of phi times sine of theta here. And then just using right triangle trig, z would have to be rho cosine of phi. Now, if you're trying to get phi back from x, y, and z, we need a formula over here as well. Like these allow us to get from rho, theta, and phi to x, y, and z. These are supposed to allow us to get from x, y, and z to rho, theta, and phi. So I think I'll just take this equation and solve it for phi, or at least solve it for cosine of phi. So we'll get z over rho but we want that in terms of x, y, and z, so we'll take the square root of that. So it's z over the square root of x squared plus y squared plus z squared is cosine of phi. So these are our coordinate conversion formulas. And these are what we will use when we want to take a triple integral written in rectangular coordinates and convert to spherical coordinates. So I think I will save that for another video, but that is your introduction to spherical coordinates. Remember, rho equals a constant. Those are spheres radiating out from the origin. Phi equals a constant. Generally, those are cones. If that angle is between 0 and pi over 2, we get a cone facing up. Angle is equal to pi over 2, we just get the xy plane. If the angle is between pi over 2 and pi, we get a cone facing down. We have some degenerate cones that are just the positive and negative z-axis, but generally, phi always goes from 0 to pi. If theta equals a constant, we've got a plane that passes through the z-axis. And if you put all those pieces together, you get something that looks like a sphere with latitude and longitude lines on it. Theta and phi give you the latitude and longitude. These blue circles correspond to constant values of phi because those are where those cones are intersecting our sphere. And when theta equals a constant, I've got planes that pass through the z-axis and they're intersecting our sphere, so we get these lines. But rho equals 3, that's telling us we start at 0, 0, 0, and we go out 3 units. If rho is equal to 2, we start at 0, 0, 0, and go out 2 units. Now that's a surface. It's not the solid sphere, it's the surface. To get the solid sphere, rho would have to take on a range of values, and we'll look at that in the next video.